You have half an hour and leave some time for questions, please.
Thank you. I'm Yasuhiro Iwamura from Tohoku University. I will talk about the recent experimental results on excess heat and other elemental analysis and gas analysis results. Here's the background of my research, our research. I was engaged in the permeation index transmutation experiment with nano-sized multilayer thin film when I was a researcher of Mitsubishi Heavy Industry. At that time, I used palladium and calcium oxide multilayer, and we put on the surface cesium barium, and we made a deuterium gas flow like this, deuterium permeation through this multilayer, and we observed the transmutation reaction. For example, cesium into praseodymium, like that. And after that, after moving to Tohoku University, I had a chance to participate in the National NATO project. And we performed the excess energy experiment with nano-sized metal composite particles. And then combine these experience. Now we develop the excess energy with nano-sized multilayer metal composite and hydrogen gas method. Now this work is collaboration with Green Planet. And my current understanding of our field is described here. A lot of experimental, solid experimental results have been obtained, and theoretical clarification are in progress. But in my opinion, experimental results up to now are still weak to declare nuclear. So we call this field phenomena quantum hydrogen energy, and research and development strategies here. So in my opinion, first priority should be to develop a practical device based on QHE and in this field. So if we if we demonstrate that the method can be practical use, practical one, people in the world would recognize the usefulness of this research in this field, and research funding will be available, and expand the number of researchers in this field, I hope. And then we will be able to clarify the reaction mechanism. Because this phenomenon is very complicated, so many researchers are necessary in this field, I think. Okay. This is our experimental method, basically the same as I presented. We use this nickel-based nano-multilayer thin film, like this, and the weight of the nickel plate is 0.1 gram, and the surface area is about 1 square centimeter. And we provide two samples. And the center, we have a ceramic heater. And we evaluate the temperature by the ceramic, some couple in the ceramic heater. And also we measure the surface temperature by a radiation thermometer and the other thermometer. Okay. And at first we make fabrication this multilayer, and we introduce the sample holder, this one, into the vacuum chamber. And then to remove the surface impurities such as water and hydrocarbons, it's very important to control surface impurity. And we bake the sample, and after that, mainly we provide hydrogen gas into the vacuum chamber. And hydrogen gas absorbed into the sample. And usually next morning, we evacuate the hydrogen gas, and simultaneously heater is on and heat up the sample. And then absorbed hydrogen in the nickel film diffused toward the vacuum side like this. And then we observe the anomalous excess heat phenomena. And sometimes we analyze the released gas by quadruple mass spectrometry. Okay, this is the model of excess heat evaluation. Because during excess heat experiments, we evacuate the hydrogen gas, so we just only think about the heat conduction from the sample holder and the thermal radiation from the surface, from the sample surface, and from the sample holder is equal or power input or and plus excess heat, if any. Okay. And actually, nickel brand, nickel plate excess produce some excess heat, but in our case, we use nickel brand run. We use the nickel as a brand run. And this one is a relationship between the sum couple and the input power. And this one is a calibration curve for nickel only. And this one is a nickel with mulch layer. If we input the same input power, we observe the temperature difference. For example, in this case, 800 degrees centigrade, and for the mulch layer, 860 degrees, something like that. So we observe the delta T. And excess heat can be expressed as a function of delta T. So this is a typical example of excess heat generation. In this figure, this is the time, and this one is excess power, and this one is pressure. And blue point means pressure in the chamber, and red point is excess power calculated by delta T. At the beginning of the experiment, we provide some pressure, hydrogen pressure, and usually in the evening we provide. And during the night, higher sample absorb the hydrogen gas like that, and then pressure of the hydrogen gas is decreased like this. And next morning, we evacuate and simultaneously input. In this case, 90 watt is provided to the sample holder, sample ceramic heater, and then in this case, we observed about the 3 watt excess power. Okay, and we repeat this process. And based on this data, we can calculate the total. We can calculate the total absorbed number of hydrogen is here. And integrating the excess power by time, we got the total energy here. So we can evaluate the excess energy density. Electron volt per hydrogen is here. So 12 keV per hydrogen is very high, because the usual chemical reaction ranges in the electron volt per hydrogen. So this phenomenon cannot be explained by known chemical reactions. Okay, and as we improve, as our experiment progress, we sometimes observe the spontaneous heat burst. And we investigate the reason for the spontaneous heat burst, and we found that the input power fluctuated slightly when we observed the spontaneous heat burst. So we tried to see if we could intentionally cause the heat burst, and so we get we gave this kind of fluctuation as perturbation, small perturbation in input power, and finally successfully induced heat burst intentionally. The data already show at the ICCF25, but again, I will explain this. This is a no heat normal case. Red one corresponds to some couple in the center, and the blue and green means the surface temperature, surface A and surface B, and here the axis. And brown is the input power we give to the ceramic heater. At this time, we reduce the input power slightly, and after 3 minutes, we return the input power like this. And then, if we decrease the input power, some couple and surface temperature, and decrease like this. And after returning to the original value, they are going back to the original value. It's very reasonable. No phenomenon occurred in this case. But if we use multi thin film like this, we give the perturbation, input power perturbation here for 3 times, and some couple decrease, and surface A and B decrease, and after returning the input power, at this point, surface temperature rapidly rise like this, and this heat propagated to the center of the heater. So increases in surface A and B temperature were larger and steeper like this than that of TC. Heat burst energy generated at the surface like this, surface, and propagated to the center of some couple. And during this process, we did not no extra energy. So, and the heat burst occurred under the same heat dissipation condition here and here. So this heat burst phenomena is not the artifact due to the calibration curve deviation or something like that. Okay. And also this heat burst, we expand the time scale, and we plot the some couple change only. And at this point, we have a heat burst here, and gradually decrease. At this point, we have a 6 watt excess heat, and at this point, at the end of the experiment, 5.6 watt. So, energy generated by a single intentionally induced heat burst should be more than this 4.8 kilojoule. Okay, but in this case, we have no gas in the chamber. At least pressure is very low. It's under less than 4 by 10 to minus mole. So if we try to explain about the heat burst by the chemical reaction like this, it is impossible, because at most chemical reaction 10 to 4th and 10 to 5th joule. So based on these data, we now have some hypothesis, this kind of hypothesis. We are now using postulating trapping hydrogen hypothesis. Because the perturbation of input power causes a fluctuation in hydrogen density or hydrogen diffusion, which might trigger the heat burst phenomena. So we postulate this kind of trapping side, hydrogen gathered into the trapping side, and at this point, heat burst, anomalous heat reactions occur. We assume now. Okay, so we are going to the recent experimental results. First one is possible excess heat rise by the combination of intentional heat bursts. Okay. I show the intentional heat burst only negative perturbation, but a combination of negative and positive perturbation of input power is useful. We said that T negative and P delta power equal T positive by delta positive. If we set this condition, given power is the same as if as P input, okay, the same as if we average. And sometimes we successfully continuously trigger heat bursts depending on the experimental conditions. Okay, I will show you the example. In this case, red one is the sum couple temperature, and blue and green is the surface temperature, and brown is the input power. As I said, we gave the negative perturbation and the positive perturbation combination like this. And then we observe the heat burst here, like this. And as you can see, continuously surface temperature and the sum couple temperature increase up by applying this combination and positive, negative and positive input power perturbations. In this case, increased energy by this combination is amount to 38 kilojoule. Okay, I'll talk about another point. Region of high oxygen concentration and excess heat. This is also presented at ICCF25. We found that some common features, characteristics of the sample in which heat was observed, excess heat was observed. We observed this kind of black spot. This is an image, compo image by backscattered electrons. Black point, black regions means light elements lighter than nickel, and actually this is the presence of oxygen. And this one also presented at ICCF24. If we look at closely by same EDX, like this, at this point, from this point, very high concentration of oxygen. But on the same one, from here, non-detection, no oxygen by this elemental EDX. And this one produce excess heat and intentional heat burst occurred sample. And this high oxygen confirmed by the depth profile by Topsham's analysis. This one is already shown. Okay, so I would like to say about the method of surface analysis. Usually, oxygen, we have many, we are surrounded by the oxygen. So it's very difficult to identify, to say about the oxygen. And usual metal, surface of the usual metal oxidized by the oxygen in the air. And XPS, this is the XPS spectrum, and we can see the clear oxygen peak because XPS can measure a few nanometers from the surface. So very thin, few nanometers are easily oxidized by the air. But we mainly use EDX. EDX measurement depth is more thicker, about a few, 1 or 2 micrometer. So for the same sample, if we measure by EDX, we cannot see much oxygen like this, because just only surface is oxidized. So usually, if we use EDX, oxygen is not detected by EDX. Okay. So I will show you the recent data. This is the control one before experiment. As you can see, at this point, we have nickel and copper. These are we provide a multilayer thin film, and carbon is impurity, and unknown also impurity, and oxygen. Huh? どうしました？あ、そうです。Okay. And this data is excess heat generated sample, about 7 watt. In this case, we observed a feature like this. And at this point, at this special point, we detect the oxygen 33.7%. But from the same one, the other point, we detect only 0.59 oxygen, okay? Like a control sample. And this one is another example. This sample generated 9 watt for larger heat generated sample. We can see a very characteristics. We see the many black spots, black part from the sample. And if we measure this sample at this point, we did not so much oxygen, but from here, 38.1%, and the other point, very high value. Okay, so for this sample, we analyze by top sinks for the same sample. Then we analyze the depth profile. This is data for before experiment, and this one is after experiment. That sample, this one. As you can see, before experiment, we gave the multilayer thin film, and this one is a nickel and copper and oxygen here. And this is a surface oxygen here, and interface oxygen here, and oxygen in nickel here. And as you can see, this is the data after experiment. As you can see, oxygen is a significant increase in oxygen concentration after experiment, very deeper region, and nickel and copper and other impurities. And also we can see copper and nickel are diffused and alloyed due to the high temperature. And also, this is the data for the surface distribution of each ion species for the same sample. Before experiment, we did not see any structure, but after experiment, this is a same image. And oxygen surface distribution here. So oxygen ion distribution after the experiment was non-uniform and observed by semi-EDX, so consistent with the semi-EDX. And I performed the experiment, expected to have a high oxygen concentration. So we gave the post-oxidation sample is here. Oxidized at 700 degrees for 2 hours in the air. And because surface temperature during experiment is about 700 degrees centigrade. After hydrogen loading, we found here, and oxygen concentration is not high, 1.78 or something like that. So even post-oxidation samples have oxygen concentration below 5% after the normal hydrogen absorption process. And this is the results of a quadruple mass spectrometer. Its main residual gas is leaked air. And the graphic pattern of leaked air is here, mainly nitrogen, 28, and the next is oxygen, 32. And relative intensity is here. And this is our data. And based on this data, mass 32 by mass 28 is equal to the matched literature value. And then I will show you the examples for large and small excess heat case. This red one is a large excess heat case, and blue is a small excess heat case. And we gave the perturbation here like this. And this one is a loading pressure. During this period, we gave the 250 Pascal hydrogen, and during this period, we gave the 30 kilopascal. And then, as you can see, excess heat a little bit larger than in the case of 250 Pascal. So weak positive correlation between hydrogen loading and pressure and excess heat. And we analyzed by quadruple mass spectrometer. It's here. Mass 32 by mass 28 to 28 is nearly O2 by M2, heat dependent. This one is a large excess heat case, and this level is a natural one, air one. As you can see, in the case of a small excess heat, almost the same in the air leak value. But in the case of large excess heat, very high value for mass 32. So mass 32 by mass 28 is larger than the value of atmospheric component from almost all the heat samples. And mass 32 by mass 28 tends to be higher for larger excess heat. So this result is consistent with the existence of a region of high concentration oxygen observed by semi-EDX, as I showed. So it's a summary of oxygen concentration. By the semi-EDX and top SIMS analysis, normal area, even in heat-producing sample, less than 1%. But we found some region, special region of high oxygen concentration at HOC in the heat-generated sample, larger than 10%. Here, like this, 38 and 21 and like this. And top SIMS image here. And highest oxygen concentration in the post-oxidation sample, less than 5%. And also, based on the quadruple mass spectrometer, values tend to be higher with more excess heat, and they are consistent with EDX. Okay. So, as I said, we are surrounded by oxygen. So, very difficult to, what's happening, this anomalous oxygen. So, we should think about, at present, 4 scenarios. One is oxygen concentrations were low during the experiment, but anomalous oxidation was induced only at certain sites, only at certain special sites. This one, these special sites, oxidized after sample removal from the vacuum chamber. Okay, and next one is by anomalous hydrates like this, hydrates formation. And the third is oxygen that originally existed in the nickel bulk, diffused only in certain areas and forming a region of high oxygen concentration during the experiment. If we accurate data that diffuse 1 and 2 and 3, we will have a possibility number 4 will emerge. Number 4 is oxygen was produced by some nuclear effect. I think that transmutation or something like that. So it's very difficult, but we should make experiments intensively and diffuse this scenario. Okay, so now we are attempting to find a quantitative correlation between excess heat and the region of high oxygen concentration. This one is an example. Analysis is compo image and the calculation of area of very high concentration, high oxygen concentration. Here we can see some very high oxygen concentration, A and B and C, and we can calculate by this. And the portion ratio of the high oxygen region by surface area is about 9.6%, like almost 10% here for the example. So now we are planning to carry out in this kind of analysis. Okay, so I would like to conclude. Nickel-based nano-sized multilayer thin film was preloaded with hydrogen gas, heated rapidly to diffuse hydrogen and induce heat generation. Cannot be explained by any known chemical process. The combination of negative and positive input power perturbations successfully increased all surface and thermocouple temperatures. This could be one method of reaction control, heat reaction control. So, in heat-generated samples, regions of very high oxygen concentration, more than 10%, were often observed. However, in the same sample, oxygen concentration were less than 1% in the non-LHOC regions. Even in forced oxidation samples, oxygen concentrations were less than 5%. These LHOCs tend to be larger with larger excess heat. And quadruple mass measurements also showed that the oxygen concentration in the gas released during the experiment tends to be higher in sample with larger excess heat. And this is acknowledgement. Thank you for your attention. Thank you.
Thank you. We have 3 minutes for questions. That means 2 short questions. Just the first, the others you can go.
Okay. Thank you, Iwamura. Very nice presentation. I have seen in a range of experiments plasma flow discharge and other experiments exploding wires where structures are formed that last for about 2 days, and they can pass through air, they can bind to metal surfaces. I can show you SEMs from 1979 right the way through to recorded last week that produce a regular array, and they can typically have these spots in them which have high oxygen or high carbon content. So, to answer your question, you said potentially it's oxidized after the event. So I would suggest that you leave the samples in the device for at least 2 days to overcome this 2-day latent period. And that's it. If you want to see any of this work and the SEMs, I can share it with you.
Okay, thank you.
One more question.
This is not a question, this is just a confirmation of your finding. We have found in our experience we've measured screening energy at different compositions of the target. So we have oxygen impurities, and what we see that the screening energy is increasing according to the higher amount of oxygen at the target surface, step by step. And the results will be presented today in the poster session. So we compared carbon and oxygen seems to be an active material for increasing all the screening energy as well.
Okay. Okay.
Okay, Sven.
Okay.
Oh, you're on.
Thank you.
Okay. Okay, thank you.
Thank you. Thank you very much.